Okay, we're on the hour here, so I think we're going to get started. I'm Becca from AGU's Media Relations Office, and along with my colleague Liza Lester, I'll be helping run this press conference. This press conference is titled Intensifying Storms and Flooding in a Changing Climate. We will begin with panelists each giving brief presentations describing their work, and then we will open it up to questions from reporters. We will end on the hour or when there are no more questions, whichever comes first. On-site reporters will be able to meet with on-site panelists in the quiet room in room R05, which is next to the press room on the second floor following the press event. Reporters, because this is a Zoom webinar, you will not be able to turn on your video or microphone without being invited to do so. So if you would like to ask a question, please type your full name and affiliation into the Q&A box, not the chat, but the Q&A box. And we will request that you unmute yourself to ask your question, or you can type in your question along with your full name and affiliation, and we will pose it to the panel on your behalf. And we'll respond to questions in the order that they were received in the Q&A box. You can write in your question at any time, but they will not be responded to until panelists have completed their presentations and we are in the Q&A portion of the press conference. And reporters, please make sure that your Zoom name is accurate so that we can easily find you in the participant list. Slides and additional materials from this briefing will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This press conference is being recorded, and the recording will be posted to AGU's YouTube channel, as well as linked to in the Press Information Exchange. Please bear with us should any technical issues arise. If the Zoom webinar goes down for some reason, we will switch to presenting this press conference through a teleconference line. If this happens, we will immediately send out an email to all the panelists and attendees with instructions on how to access the teleconference line. Otherwise, if you have any technical issues during this press conference, please email news@agu.org. And with that, I'll turn it over to today's panelists.
Okay, hello everyone. Can you hear me all right? So my name is Eric J. Shearer. I'm a doctoral candidate at UC Irvine. Today I will present findings from my research entitled Trend Analysis of Global Tropical Cyclone Precipitation using High Resolution Climate Data Record. Below you can find my contact information along with my research center's homepage. Go ahead and click. My work focuses on precipitation from large storms known as tropical cyclones, which are also called hurricanes, typhoons, or tropical storms and depressions. While recent work over the last decade has shown intensification in tropical cyclones, these studies are mostly focused on wind from these storms, not rainfall. In rainfall, we have yet to detect any changes over the historical period. In this study, however, we do find that the rainfall rate has increased in global tropical cyclones over the past few decades. In the figure I'm showing on the screen, we observe an 8.5% increase in rainfall per degree Celsius of global sea surface temperature warming, which meets our expectation for changes in rainfall from warming oceans. Warming oceans have been shown to be caused by human activity. So in this study, we hypothesize that rainfall has increased because of human activity as well. Next slide. The backbone of this study is new high resolution data of rainfall, which goes back to the 1980s. High resolution means the data has great amount of spatial density and frequently occurring measurements. In this figure, we plot 2017's Hurricane Harvey, which infamously dropped over 1 meter of rainfall over the Houston metropolitan area. Here we see that our new high resolution data is able to capture these regions of high intensity, which are symbolized by the yellow color. Before this data was created, the only high resolution data sources we had did not extend far back enough to overcome natural variability in the Earth's climate, which experiences decades-long shifts from the norm. Next slide. Because we see increased rainfall rates, we expect to see increases in the rainfall totals from tropical cyclones, that is the total volume of precipitation per tropical cyclone event. In this figure, we do see positive trends, shown in red, exist in some basins like the North Atlantic, South Indian, and South Pacific. Click forward. Along with globally. Globally, we see a change in tropical cyclone volume at a rate of about 0.28% a year or 12% over 40 years. Next slide. It's important to note that these changes haven't occurred evenly across the globe. Depending on where you are and what strength the storms are, these changes can vary widely. For example, in the previous slide, we saw that not every basin has seen an increase in the raininess per tropical cyclone event. On this slide, in the figure, we look at changes in the rainfall rate from tropical cyclones in the North Atlantic Basin, where New Orleans and AGU is this year. Here we see an 8% decrease in storms that do not become hurricanes, while we do see an increase of about 13% in rainfall rates of hurricane strength storms. Next slide. Lastly, though we do see global increases in tropical cyclone rainfall, its effects have only been seen in a few locations. In this figure, we see that the only statistically significant increases in year-to-year rainfall totals over land is in North America and India. It might initially seem unclear why this is the case, but the reality is that a lot of rainfall from tropical cyclones fall over the ocean before making landfall. Next slide. Next slide. Okay, so thank you for your attention. I look forward to all your questions.
Okay. Hello, everyone. I'm Kaoru Kakinuma from Shanghai University and Tohoku University. I would like to talk about global flood impacts on population displacement. This study was conducted by following researchers. Next slide, please. So our biggest conclusion is countries in Africa face a high likelihood of flood-induced displacement. This map includes two variables. One is global flood-induced displacement. Another one is flood-exposed population during 2008 to 2013. So here, flood-exposed population means the number of population who are potentially affected by flood. So please see red color region. Red color region are found mainly in Africa. For example, Burkina Faso, Mauritania, and Ghana. These countries have low flood exposure, but high flood-induced displacement. So red color region might be highly vulnerable to flood because they have relatively large number of displacement, even at small floods. And please see the purple color region, including India, China, and the Philippines. These countries have high flood exposure and high flood-induced displacement. That means purple color region are facing large magnitude of flood. And finally, blue color region, including Netherlands and Finland. These blue color region have high flood exposure, but low flood-induced displacement. That means blue color region might successfully mitigate the impact of flood on population displacement. Next slide, please. And we also found large gaps in flood-induced displacement between high and low-income countries. This figure, x-axis shows income level of each country, and the y-axis shows flood-induced displacement, and each dot means each country. The relationship between income level and displacement is nonlinear. And as you can see, high-income countries have low flood-induced displacement, but on the other hand, some of low-income countries have high flood-induced displacement. That means there are large inequality in flood-induced displacement between high and low-income countries. Next slide, please. So why our finding is important? We showed areas where flood have a significant impact on population displacement. So flood magnitude and frequency are estimated by other studies by using hydrological modeling or satellite imagery analysis. However, the social impact of floods varies among countries. So each country has different social cultural background and different history of flood. So combination of hydrological, demographic, and economic data are essential to estimate the flood risk on society. So the collaboration study can identify and support regions at high risk of flood-induced displacement. Next slide, please. I also briefly introduce how did we make a map. So firstly, we calculated potential flooded area by using global river and inundation model. We overlay flooded area with population data to get flood-exposed population. We also get data of flood-induced displacement. This is observation data, which are provided by internal displacement monitoring center. We use these two variables, flood exposed population and flood induced displacement, to make bivariate map. Next slide, please. So if this is my contact address, so if you are interested in our research, please feel free to contact me. Thank you.
Okay, hello everybody. I'm Greg Foltz, so I'm at NOAA's Atlantic Oceanographic and Meteorological Laboratory in Miami. And I'll talk about predicting rapid intensification of hurricanes, and specifically why ocean salinity observations are important for improving forecasts of rapid intensification. Next slide, please. Okay, so hurricane forecasters and researchers normally define intensification by the maximum wind speed. And rapid intensification is an increase in that maximum wind speed of at least 35 miles per hour over a period of 24 hours or less. And actually pretty much all intense hurricanes, so all category 4 and 5 hurricanes undergo rapid intensification at some point during their lifetimes to bring them up to that high intensity. So this means that these storms can be have particularly strong impacts if they make landfall. And that's especially true if they intensify rapidly immediately before landfall. And this happened with Hurricane Michael, shown here in the Gulf of Mexico in 2018. So it intensified rapidly and up to a category 5 and made landfall in Florida. And it was associated, caused 16 deaths and $25 billion in damages. And this was not a well-predicted extreme event. So it's important to be able to improve predictions of this. There are also indications that climate change will make rapid intensification more likely to happen. So as an example, currently there's about 1 every 100 years we'll have an extreme intensification event of 75 miles per hour in a period of 24 hours. And under climate change in the year 2100, that's projected to happen about once every 5 to 10 years. So that's about a 10 to 20 times increase in the likelihood of this extreme event happening. Next, please. Okay, so the ocean, we know the ocean is important, and specifically the temperature. So the surface temperature of the ocean, if it's warmer, it makes rapid intensification more likely. There's more fuel, more energy that can be transferred to the hurricane. And this is especially true if that heat extends, the warmth extends into the subsurface ocean. So if there's high upper ocean heat content, this is more likely for rapid intensification to occur. And the heat content tends to be highest in the Western Caribbean Sea, shown here. Go to the next slide, please. So our new research is showing that in addition to the well-known effect of temperature, that ocean salinity can also be important for a rapid intensification. And this is especially true in the Western Atlantic and the Eastern Caribbean. So you can see there's low salinity. This is caused by outflow from the Amazon and Orinoco rivers. And this creates a fresher layer, a fresh lens near the surface of the ocean. And we found that this can make rapid intensification more likely. So, and this is an important region. So the hurricanes can intensify rapidly here before they make landfall in the Caribbean islands or the southeastern United States. An example is Hurricane Irma in 2017, which did just that. Okay, next, please. All right, so we know that all storms need warmth. They need ocean heat content, higher ocean heat content. And so our new results are showing that rapidly intensifying storms tend to have a lower surface salinity on average compared to those that do not. And this is related to an increase of salinity with depth in the ocean. And both of these then combine to act like a barrier. So this is a barrier to the mixing up of colder water from underneath, from deeper in the ocean. And when it prevents this mixing up of colder water, the surface of the ocean stays warmer as the hurricane goes by. And this provides more energy, more fuel to the hurricane and makes it more likely to rapidly intensify. So the summary is that we found that a lower surface salinity makes rapid intensification more likely to happen. Next slide, please. Okay, so it's important to be able to improve predictions of rapid intensification, and largely because it can be so dangerous if it happens close to landfall. And so it's really a top research and operational priority to improve rapid intensification forecast and understanding. We did experiments with a forecast model, just adding surface salinity to the model as a predictor, and we found significant improvements in the ability to predict whether rapid intensification will occur or not. So this has promise for improving operational forecasts of rapid intensification in the Atlantic. This also shows a need for high quality in situ data of salinity, especially ahead of storms. So if we have this, then we can know, it can inform us whether it might be more likely for a storm to undergo rapid intensification. And currently, satellite salinity data is not able to be incorporated into operational forecast models. So really, the in situ salinity data is all that we have. And we've partnered, NOAA's partnered with Saildrone to obtain some of this important high quality in situ salinity data. Next slide, please. So this is an example of some Saildrone. So NOAA again partnered with Saildrone, and during this past hurricane season, during the peak of the hurricane season, we sent 5 Saildrones out in the Western Atlantic and the Caribbean Sea. This shows 3 of them. They obtained high quality, important data from the ocean and atmosphere to help us better understand and predict rapid intensification. And so Chris Meinig in the next talk will give more details of uncrewed technology like Saildrones. And I believe next we'll see a video from one of these Saildrones that went through a Category 4 hurricane, the first time an uncrewed surface ocean vehicle obtained video from the inside of a major hurricane. Thank you.
Hi, good morning, everyone, and thanks so much for the invitation. It's wonderful to be here with you today. I hope that video didn't get you seasick first thing, off our bat here. My name is Chris Meinig, and I'm Director of Engineering at NOAA's Pacific Marine Environmental Lab. And I'll be talking about using uncrewed systems like we just saw there to advance extreme weather prediction. Next slide, please. So why use uncrewed systems? Why are we doing this at all? Well, we feel like there are fundamental advantages in using those, and we can further our advanced understanding of rapid intensification, like the problems that Greg showed us, where we can understand more about salinity in broad ocean areas to improve these forecast models. And importantly, we're able to measure these ocean and air properties that are not observable today by satellite. So this gives us additional assets in the water to provide data. Also, these are remotely piloted, so people are not put at risk. And when we combine these assets all together, we can really do revolutionary things. Importantly, this is right in the core sweet spot of NOAA's mission, which is to understand and predict the changes in climate and weather in oceans and coasts, and to advance our forecast systems to protect lives and properties. Next slide, please. Now, what you're seeing here is the Saildrone that took the video in Hurricane Sam. And this is specifically designed to survive hurricanes. This is the product of years of innovation through public-private partnerships, where we harness the best of private companies and government towards a shared vision. Importantly, if you look at this Saildrone, the vertical wing, we call it a wing or sail, has been significantly hardened and shortened from traditional designs. Now, we learned that through actual ocean work in order to survive. Really, it's not the wind, it's the water that causes the most force on these Saildrones. Saildrone did a wonderful job of specifically designing these so these could be tumbled and rolled in these extreme ocean waves that we saw, and that in fact all of the 12 sensors that you're seeing there are really key to doing that. And for Hurricane Sam, all of them survived, which is really a remarkable feat in getting real-time data back from some of the most hostile environments on the planet. Next slide, please. This is storm chasing on a massive scale. This is the first time that we've combined the video and air sea flux sensors that have been observed from an uncrewed surface vehicle. In the upper left, you'll see the Saildrone in the 12 o'clock position. Now, we purposefully piloted the vehicle in that position to get the worst of what the hurricane could give us. Putting it in harm's way is really going to stress test the technology to help us understand and advance the technology after our first year. This is the first year we were in the water. And for Sam, the story went something like we had about a week heads up where researchers like Greg were able to work with the pilots and pre-position it based on best available forecast track estimate, so that we tuned this on a daily, hourly basis and trying to get the hurricane right in the northeast quadrant in order to experience these extreme winds. And we were basically lucky in this year where we had 3 hurricanes and also 3 tropical storms for our Saildrones that were encountered. We very much take this as a technology that has can advance our future, but it's not the only thing out there that we're using to improve hurricane forecasts. Next slide, please. Now, to be better prepared, we're using a variety of systems. What you're seeing here is an underwater glider. Now, these can be deployed from small boats during times of good weather when we're not experiencing the hurricane, and they have long, persistent timescales. Now, these give us a glimpse of the interior of the ocean, measuring both heat and salinity. They travel down to 3,000 meters, and they make sawtooth profiles of giving these important parameters that satellites cannot see. This is basically the fuel that's behind the hurricane, and when we combine that with both surface properties and satellites, it gives us a better picture of completely what's going on. We do this with NOAA and our partners, and we deploy these in tandem for the first time with our uncrewed surface vehicles. So 3 of the Saildrones were coupled together with these gliders, and we tried to keep them on track and close together so that we can have a full understanding of what the air-sea properties are to advance our rapid intensification, our basic understanding of rapid intensification. Next slide, please. As extreme events increase with global warming, our vision is to expand this and to be better prepared for our hurricane observations. And in fact, many other extreme events where we would couple these with air-launched aerial drones and coordinate with additional profilers that could be thrown out of the P3 that you see here out of the aircraft. And our vision is to integrate these real-time measurements into forecast models. By co-locating these measurements together, in a coordinated fashion in a box there, you see something like 6 miles wide, 1.3 miles in the ocean depth, and 2 miles above. These closely couple with the way models work. So we're combining actual in situ ocean and aerial measurements that can advance our models. Ultimately, by continuing to innovate together as the science and engineers, pilots, governments, academia, in industry, we can push the limit of what's possible to advance the science and engineering to make everyday lives better. As these extreme events increase over time, as we heard today, we can advance the forecast models that will save lives and property. So thank you very much. There'll be some links available in which you'll be able to get background material that'll be posted after the press conference. So thank you.
Thank you to our panelists. We'll now start the question and answer part of our session. Reporters, as a reminder, you can drop your name and your affiliation into the Q&A box if you would like to ask a question, and we will invite you to open your mic. Or if you would prefer, you can type your question and we read it for you. Our first question will be from Seth Borenstein with the Associated Press. Seth, go ahead when you're ready.
Thank you. 2 questions. Very quick one for Eric. In terms of you say this is the first study to find rainfall changes. I mean, there were a whole host of studies after Harvey, Emmanuel, the Texas climatologist, Gammon. So I'm a little confused on how you can claim this is the first rainfall study. And then for Greg, please forgive me, I got called away in the beginning of your session. Can you just explain the connection between salinity and intensity and just why there is that connection? Thank you.
Hey, Seth, thanks for that question, and thanks for giving me a chance to clarify a bit. I want to be absolutely clear that regionally, these changes have been shown again and again and again regionally. My study is global in its approach. I look at storms from all across the globe, North Atlantic, the storms that affect Australia or India or the South Pacific Islands. I group them together and consider them as a whole and look to see if these changes have occurred globally over a period long enough that we who study climatology would agree is long enough to overcome the fundamental variability in the climate. There was another study, Guzman and Jing, 2021, that did look at rainfall rates over the past 20 years, and they found an increase, but in our study, we said that we wanted to look at least 30 years of data before we could make such conclusions, and we ended up looking at 40. So that's why I make that claim. Thank you.
Okay, yeah, so hi, Seth. So basically the way that salinity affects intensification is it decreases the ocean cooling that the storms themselves induce. So as a storm goes by, there's a lot of violent mixing in the ocean, and that brings up colder water. With salinity there, it decreases that mixing. It decreases the ability of the storm to mix up that colder water. It makes the ocean more stable. So that's the way that it does it. So then there's a warmer surface of the ocean as the storm passes by. And we found that this effect is really only there for the high intensification rates, not so much for the lower intensification rates. And that's because at these high intensification rates, they're extracting a lot of energy from the ocean. So the surface of the ocean really matters. And salinity can act to keep that surface of the ocean warmer by reducing the cooling. And the other is that as storms intensify, they mix deeper. Obviously, they're getting more intense. So those winds can mix deeper, and then the ocean structure matters more. So it can actually have a significant impact on the SST, the surface temperature cooling.
And just to follow up, and forgive me, I know you may have addressed, but isn't the salinity globally changing isn't it becoming less saline because of the increase of melt from places like Greenland and other glaciers? So wouldn't that have a decreasing effect in general on intensification?
Yeah, right. So that's true. In kind of the subpolar regions with ice melt, it's making it fresher. And overall, globally, we've seen it kind of an intensification of the hydrological cycle, right? So there's more rain, tends to be more rain, increasing rain in the tropics and increasing evaporation in the subtropics. So it's kind of amplifying the salinity pattern. So it's an unknown, though. I mean, that's active research. We're trying to figure out how climate change might affect tropical cyclones through changes in salinity, right? I don't think that's been looked at in detail. And the other way is that increasing rainfall, right? We heard increasing rainfall from tropical cyclones. That can also that affects the salinity too. So that's another way. Potentially, the climate change could affect salinity and then affect tropical cyclone intensity.
Thank you.
Our next question is for Kaoru Kakinuma from Craig Miller at PBS Next Avenue. He asks, how do you define population displacement? Does it include temporary dislocations from extreme events?
Thank you for the question. So our research follows a definition of displacement that's defined by the internal displacement monitoring center. And as you mentioned, yes, this displacement includes just evacuation. So it's kind of really broad definition. Is this answer to your question?
We'll see if he follows up. Thank you, Kaoru.
Okay, okay.
Next question is from freelancer Richard Levitt. What effect will climate change have on salinity? And we've already addressed this a little bit, but I'll give Greg another chance. What will the flows from big rivers increase, extending the low salinity patch?
Yeah, so climate change, let's see. So we actually found in one of our previous studies in the Western Pacific, so not in the Atlantic, but in the Western Pacific, as I said before, there's been an intensification with climate change, intensification of the hydrological cycle. And that's caused more rainfall in the Western Pacific in the areas where a lot of typhoons pass. That's freshened the surface. And our study showed that has contributed to an increase in the intensity of super typhoons in that area. So that's one way, directly through the salinity in the ocean through rainfall. The other potential way, and I don't think this has been looked at, is through, we know there are more extreme droughts and floods in South America, the Amazon, most likely due to climate change. So that can impact, you get more rainfall over land, and then the river outflow, the Amazon, Orinoco, they can dump out more fresh water or less, right, more extremes, and that can influence hurricanes that way.
And Richard had a follow-up to that first question. Are there other ocean basins where large freshwater flows could produce rapid intensification?
So the Bay of Bengal and the Indian Ocean has a huge freshwater signal in the northern Bay of Bengal. So that's actually a big, that can have a big impact on storms and as they threaten landfall in a pretty vulnerable area. So that's another area besides the Atlantic. But the problem is, so there's not a lot of data. There are not a lot of tropical cyclones that pass through the Bay of Bengal. So that sample size is very limited. So we didn't find a robust signal there. We did find a signal, but not as robust as in the Atlantic because there are a lot more storms passing through.
Question for Eric from Richard Levitt. How did you get your Finescale data set from the 1980s?
Hey, thanks for the question. And again, thank you for the opportunity to clarify just a little bit more. So I am part of a research group at UC Irvine that primarily is interested in using satellite measurements to do rainfall estimates. So we have accessed an archive of infrared data that's cloud top temperature data measured by infrared from geo-orbiting satellites. And from that record that goes back to the 1980s, we produce precipitation estimates from that. This is usually done with machine learning techniques. It's validated against, or it's corrected against other products from our friends at NOAA. And we have a storied history of creating these products, improving them, making them better. So I encourage you to check out our homepage if you have any questions. Thank you.
Do we have any further questions from our reporters in the audience? I'd like to thank our panelists. I'm going to close the Q&A session now, and I'll turn the mic over to Becca for closing comments.
Thanks, Liza, and thanks again to our panelists and for all the reporters who attended this press conference. I just want to note that our next press event today is a press conference on wildfires and climate change, and that will begin at 1 p.m. Central Time. Thanks again, and hope to see you there.